The expansion of four-dimensional space-time is a pretty hard concept to grasp. There was a rather large paradigm shift in terms of thinking on the structure of the universe. To try and understand this, a quick chemistry lesson is needed. Atoms are composed of three particles: protons, which are found in the nucleus and have positive charge; neutrons, which have no charge and are found in the nucleus; electrons, which have a negative charge and are found in orbits around the nucleus. These three particles compose all of the elements in the universe. The atoms differ in the way these particles group together. As the resolution of monitoring equipment improved, it was discovered that the so-called smallest particles of matter were themselves composed of even smaller particles. This was formalized in the 1960s by Murray Gell-Mann and George Zweig. These particles were called quarks. There are 6 basic quarks: up, down, charm, strange, top, bottom. A proton is made of 3 quarks: 2 up quarks and 1 down quark, one of which is red, 1 blue and 1 green. These quarks have charges that are fractions of the units of charge experienced by electrons and protons. Because of this, they can only exist as triplets in which the total charge is equal to 1. The Hubble Deep Field picture gave a glimpse into the scope of the universe. In one small section of the universe are a myriad of weird shapes and interesting visages. Here we will try and see how it all began. 15 billion years ago, all the matter in the universe is thought to have been condensed into an area smaller than an electron. This mass was highly unstable and started expanding rapidly. After this initial expansion, things were a little hot. It was so hot that it wasn't until 3 minutes after the bang that it was cool enough for protons, neutrons, electrons and other simple particles, hydrogen, less than tag. It equals 5 duration equals 1000/ greater than helium and lithium nuclei to form. A glimpse of this has been seen by looking at the amount of cosmic background radiation. While the universe expanded, its total amount of energy remained relatively stable. This meant that the total energy per area unit decreased. That is, the average temperature of the universe decreased. A snapshot of this was taken by NASA's Cosmic Background Explorer satellite. The images it took represent what the universe was thought to be like 300,000 years after the Big Bang. The image showed very tiny changes in the average temperature of the universe at that time. These fluctuations were probably what caused galaxies and stars to form. That is, there was an extremely slight fluctuation in the density of matter across the universe. It took a further 500,000 years before it cooled down enough for atoms to form. As this kinetic energy dropped, gravity was able to start using its influence more. Particles began to coalesce and form larger gatherings of matter. At one point, the gravitational forces are so great that much of the surrounding matter coalesces. As these particles clump together, they start bumping into each other, increasing the amount of heat energy due to friction. The amount of frictional energy eventually was so great that nuclear reactions started forming the first stars. Essentially, at the start, the universe was composed purely of energy. As the universe expanded, the average temperature across the universe decreased, allowing some of this energy to form matter. Einstein used this interchangeability of energy and matter as the basis of his most famous equation: E is equal to mc². When atomic nuclei form, the mass of the nuclei differs slightly from the actual mass of its constituent particles. This difference is converted to energy according to the formula. A small amount of mass multiplied by the speed of light squared is a large amount of energy.